Okay, so hello everyone again. This is lecture 6 from Work, Energy and Power. So, in this, we will be starting again with the discussion we left in the last lecture, which was regarding one of the examples about the conservation of mechanical energy. So, let's start with that. Please try to understand that question very carefully. It holds majority of the concept which we have understood till now. Okay, let us begin. So, I'm Samir Lawankar. This is lecture number 6 from Work, Energy and Power. Let's begin our discussion. So currently we are on this eighth topic of conservation of mechanical energy. So let's start the discussion directly. We can explain the course outline in the next chapter. We can do a quick revision in the next part of the lecture series. Okay. So the conservation of mechanical energy simply states that the energy of or the total mechanical energy of the system, that is basically the summation of the kinetic energy and the potential energy, is always constant as long as the forces exerted on the object are conservative forces. So we understood different definitions of the conservative forces also. So this was the first definition, which was regarding or relating the potential energy with it. This was the second definition, which was regarding about the endpoints, which was regarding the endpoints, and then we understood third thing, which was regarding a closed point. Okay. Then we understood that what is the principle of conservation of total mechanical energy. The principle of total mechanical energy states that the total mechanical energy of a system is conserved. When it is conserved, if the forces doing work on it are conservative. Okay, so if the forces doing work on it are conservative, and the total mechanical energy of a system is conserved. Okay. So these are discussions were explained in the previous lecture only. Let us start with this discussion now. Okay. So a bob of mass m is suspended by a light string of length l. So there is a bob of mass m, and it is suspended by a light string of length l, and it is being imparted a horizontal velocity. So as you can see that this is the horizontal velocity imparted into it, which is velocity v0. Next thing is such that it completes a semicircular trajectory in the vertical plane. It completes a trajectory which is semicircular, so it reaches till this location, such that where it was written. So it completes semicircular trajectory in the vertical plane with the string becoming slack. So what does it mean by becoming slack? Only on reaching the topmost point C. So at this point C, the length, so the rope or the string became slack. The meaning of slack in physical terms or physics term can be explained as the tension which is acting, the tension which was acting at this location, which is equal to 0. Okay, so there is no only gravitational force is being acting on this location. There is no another force being acted upon at this location. Okay, so that's how we can understand this. Okay. Next thing is, this is shown in the figure, that is also in the figure. Now we need to do three things. First of all, we need to obtain the expression for V0. Second thing is, so basically relating energies or potential energy with velocity value. The speeds at points B and C. So this is halfmost point, which is B, and the topmost point is C. And last is the ratios of the kinetic energies at KB and KC. So KB by KC and B and C. Comment on the nature of the trajectory of the bob after it reaches the point C. So that all things are just explanation part. Let us first understand the velocities and the ratios of the kinetic energy. Okay. So basically, so let me first iterate till this point, and then I can make you understand by solving it. Okay. So there are two external forces. I just explained to you. So there are two external forces on this bob. So please look at this location very carefully. So what is happening at this location? So there's a bob here on which a gravitational force is acting. So what is gravitational force being acted upon? It is m multiplied by g. Correct? And what is the tensile force acting on it, or the upward force acting on it? It is nothing but T, that is tension at A. Okay. So the force which the rope provides to a ball, let us say here, is also called as tension force. This is basically a tension force here. Okay. You will understand more about tension force in the subsequent chapters. Okay. So what are the two external forces here? One is gravity and the tension in the string. Okay. The latter does no work since the displacement of the latter. So basically it's talking about tension. So tension does no work since the displacement of the bob is always normal to the string. Okay, let us understand this line very carefully. Okay, so clearly see what is the direction of tension. It is always towards the center. It is always towards the center. Correct. Now, what is the direction of velocity here? So, direction of velocity is in this direction. If the velocity is acted in this direction, at an infinitesimal location, what is the direction of displacement? The direction of displacement is also in this direction. Correct. Now, please look at the definition of work. What is definition of work? It's nothing but force into cross product with displacement. Correct. What is the force here? We need to calculate about its tension force multiplied by displacement, that is delta x. What is the angle between them? Clearly the angle is 90 degrees. So it's cos of 90 as the work done at. So now you take at any location. Let us take at this location. The tension force is like this. The velocity is tangential and the displacement is also tangential. You take at this location also. The tension force is like this. The velocity is like this and the displacement is also like this. So at each and every location, the value of the displacement, the direction of displacement is always perpendicular to tension. Therefore, the work done due to tensile force will be equal to 0. Hence, the only work done is due to the gravity. So I hope you understand this thing. Let us understand more. Okay. So we understood that there are two external forces, but the latter does no work. So that does no work. Why? Since the displacement of the bob is always normal to the string. Okay. Now, the potential energy of the bob is thus associated with the gravitational force only. Quite evident, because there is no other force acting. The potential energy will only be due to the gravitational force. Okay. Thus, now first let us calculate total mechanical. So, thus the total mechanical energy in the system is conserved. Why? Because only the forces acting on the bob are gravitational force, which is doing work, and gravitational force is the conservative force. So because gravitational force is a conservative force, we can say that the total mechanical energy is conserved. So total mechanical energy is conserved. The value of the total mechanical energy at each of these locations is same. Okay, right. Let us understand now the complete procedure. Okay, so first of all, let us calculate the value of potential energy here. Let us suppose we take the datum as this location only. So we are calculating the value of H for potential energy from this location. Okay, so let us first calculate the total mechanical energy for A. So we can write total mechanical energy at A is equal to the sum of kinetic energy plus potential energy. What is kinetic energy here? It's half m into v square. So why can we take this value? Because the displacement and the kinetic energy, the displacement and the force which is being acted upon here due to velocity is in the same direction. So we can take this into consideration. But the potential energy is 0. You can see clearly the potential energy is 0. Why? Because the x value or the h value is 0. So we can directly assume v naught. Okay. So this is the first thing which we got. Okay. The second thing what we can do, if I make a free body diagram. So in the chapter of Newton's laws of motion, they've understood the concept of free body diagram. Correct? So if I make a free body diagram for the bob at this location, okay. So let us say this is the bob. Now what will be the force acting downwards? It will be nothing but mass into gravity. Correct? Gravitational force. What will be the force acting upwards? It will be tension. Correct? Okay. Now in the chapter motion in a plane. We have understood under the concept uniform circular motion. That the acceleration or the centripetal acceleration for a circular motion is equal to velocity squared divided by the radius. Correct? So here also we know that there is a movement happening so there is an acceleration happening in this direction. This is basically a AC. Correct? So what we can write? So let us take the direction of towards the center as positive. So I am taking this as positive. Therefore, what we can write? We can write that TA minus mg is nothing but equal to mass into acceleration. What is acceleration here? So it's velocity squared divided by L. So I hope the how does this equation came is clear to you. Okay. So what are the two concepts I used? The first concept I used was about FBD. What is FBD? FBD is basically free body diagram. The concept you understood in the chapter laws of motion. The second thing I understood and made you understand was in the chapter motion in a plane. In the last discussion, the last concept was about uniform circular motion. In uniform circular motion, we understood that the acceleration of a circular motion is always toward the center. What is its value? Its value is equal to EC, which is equal to, it's called a centripetal acceleration, is equal to V square by R. Okay, so therefore here the action is toward acceleration is towards center. So then what we can write? We can write TA minus mg, because my mg is in opposite direction, is equal to m into acceleration. What is the acceleration value? It's v square by r. What is r here? R is x. Okay. So therefore, this is the first equation which we got, and this is the second equation which we got. Okay. Fine. So till now we have these two equations. So let me just rub it from here. That is because that is only written here directly. So we know that E is nothing but equal to half mv naught square. And second thing is from the Newton's second law, we got TA minus mg is equal to mv naught square by L. Okay, where TA is what? The tension in the string at A. Okay, now let us calculate these all values at C also. Okay, so let us first make a diagram here again. So let us take, okay, let me make the FBD here, because this place can be used for finding out the value of. So let us make an FBD here. Okay, so this is the mass M. Where will your gravitational force act? Gravitational force will act in this direction. Okay, and the tensile force will also act in this direction. Let us say it as TC. But it is written here that with the string becoming slack only on reaching the topmost point C. What does it mean? That the value of TC is equal to 0. Okay. What is the acceleration at this point? Its A, acceleration is A only towards the center. Okay, centripetal acceleration. Now let us calculate again the value of E and Newton. Let us apply Newton's second. Okay. So first of all, calculating the value of total mechanical energy. What is total mechanical energy at this location? It's nothing but equal to some kinetic energy plus some potential energy. What is kinetic energy here? It's half m into velocity at this location, that is vc squared. Hope it is clear to you. Plus what? Now there will be some potential energy also. That will be nothing but due to gravitation. It's mg. What is the complete length from this location to this location? It's twice n. Okay, so it's 2n. Okay, so I hope the first equation is clear to you how we calculated this value. That is nothing but the summation of your kinetic energy plus potential energy. Therefore, it's half mvc square plus mg into 2n. Clear? Now let us look at this FBD. So if we look at this FBD very clearly, what we can get? We can get that mg is equal to mvc square divided by L. Okay, so this is your first equation and this is your second equation. Okay, for points. So till now we have 4 equations with us. The first equation was regarding total mechanical energy at A. The second was about Newton's second law. So till now we have the first equation, that is energy for energy at A. The second we have energy at applying Newton's second law at point A. Then next we have again total mechanical energy at C and applying Newton's second law at C. Okay, so these are the 4 equations. I explained to you how these equations came. Now what we need to do? Now just do, okay, so how should I need to explain this to you? Okay, so now what we are doing is, let me use the black slide for that. Okay, so just look at this line very carefully. Okay, so for point C, what was happening? Only mg was acting at this location and the acceleration was also at this location. Correct? So what was the first thing we got? We got that total mechanical energy is nothing but equal to E, which is equal to your m G into 2L plus half M into VC square. Correct? So it's VC square. And the second thing which we got was the mg is nothing but equal to m into vc square by l. Okay, I hope it is clear. And similarly for the lowest most point, what we got, that this is the value of mg. Okay, this is the tensile force acting on it. This was the acceleration at that point. So AC has subscript C depends on centripetal value. Okay, so it's C, it is the denotation of C. So here what we got energy as half m v naught square, correct? And similarly we got Ta minus mg is equal to m v naught square by m. Okay, so now we can equate this equation number 1 with this equation number 2. Let us equate it. So what we will got, we will get, what we'll get, we get mg into 2L, correct, plus half m in the place of so from this equation we can get that nothing Vc square is nothing but equal to Gl, correct? Vc square is nothing but equal to Gl. So in the place of Vc square I can write Gl directly, correct, which is equal to half m v naught square. Okay, so this is nothing but this equation and this is nothing but this equation. Only I used this equation also. Okay, so this is nothing but I used this line here. I used E is equal to half v naught square here and the first equation at this location. Okay, I think it is clear till this location. Now let me just do more simplification. So let me take mgl as constant. If I take mgl as constant, I will get 2 plus 1 by 2 here is equal to 1 by 2 into m into v naught square. Okay, just cancel m and m from both locations. Now look at this very clearly. Okay, so I'm just doing mathematical formulation now. So gl into 5 by 2 is equal to v naught square by 2. 2 getting cancelled. Therefore, velocity v naught is equal to under root of 5gl. So that's how you get the first value of velocity, which is v naught is equal to under root of 5gl. I hope it is clear. I will try to explain again. So these were equations which we got for the top value. These were the equations which we got for the bottom value. Correct? Then I just let me change the color so that it can be highlighted more easily. So using this equation number 1 here, correct? So this was equation number 1 put up here. Because the total mechanical energy is same, I just equated both these equations. This equation has been used up here. That is half m v naught square. Hope it is clear. Now in the place of this vc square, as we knew that from this equation here, we can write this to be equal to vc square is equal to gl. So I just wrote this value of gl at this location, and then just simple mathematical manipulations gave us 5gl is equal to v naught square. Hence we got v naught value is equal to under root of 5gl. Okay, so I hope it is clear. And that is the first expression which we will get today. That is nothing but v naught is nothing but equal to under root of 5gl. Therefore, if a question is being asked to you in which a bob is being set up or given imparted a horizontal velocity from the lowest most position, and you are being asked and it is being said that it loses its tension or the string becomes slack on reaching the topmost point, then what we can say? We can say that the velocity with which it was being imparted was equal to under root of 5gl. So length, you would have known, let us say length is 1 meters. Let us take, then what should be the velocity? The velocity will be equal to 5 into 9.8. Okay, so this should be the velocity. So I hope it is clear till this position how we obtained everything. So the only way to obtain it was so that we can consider, or basically the concept of conservation of mechanical energy will be used here, and previous concepts such as uniform circular motions, acceleration, and Newton's second law of motion will be used. Okay, so I hope that thing is explained. Let's move on. So now from again from the energy concept which was being implied here and the Newton's second law of motion which was being implied here, what we got? We got that mg is nothing but equal to mv square by r. So it's vc square by n. Mm getting cancelled. Therefore, we got the velocity at the c location is nothing but equal to under root gl. Okay. So you can see clearly, you can see very clearly here that first of all, the velocity at this location is equal to what? It's under root 5gl. On reaching to this point, it is being reduced to g into l. Okay, the velocity keeps on reducing, but please remember very clearly, the acceleration is always constant. And that is the only reason why we can directly apply the concept of uniform circular motion. Okay, so that is the reason you need to understand each and every concept from the first lecture of the physics, so that you can understand how a cycle is being is being going on. Okay, so we started with basic discussions of force is equal to mass into acceleration, also under the uniform circular motion, and now we are understanding energy, work, energy, and power, in which we directly applied both the previous concepts here. Okay, so you can understand that the velocity was under root 5gl here, but when it reached this point c location, it was reduced to under root g. Okay, fine. So we understood these all things. Now let us understand the same thing for this energy p location. Okay, fine. So let us first of all make a free body diagram. So if I make a free body diagram for this location, what will happen? What is the mass? Mg here. Mg is in this direction, and tension is in this direction. So tension will be TB. Okay, and acceleration will be in this direction with, let's say, AC. Correct? Right. Similarly, let us calculate the energy first. So energy is nothing but equal to V plus kinetic energy. Correct? What is potential energy here? It's mg. What is the length or what is the height? It's just L plus half m v b square. Correct? So now either you can equate it with energy at this location, or you can equate with energy at this location, because the energy is same always. Okay, let us calculate with the energy at this location only, because we directly know the velocity at this location. So it is nothing but equal to half m. What is vc square? We know it's nothing but 5gl. We just calculated it. It's 5gl. Okay, so therefore we can directly calculate vb. So I'm just applying this concept here. So energy at C is nothing but equal to half m into Vc square. We know Vc square is nothing but equal to 5gl. Therefore, Ec is equal to half m into 5gl, or it is written as 5mgl by 2. Okay, so this is easy. Similarly, I can also write what is the value of Vc will be not 5gl, it will be, I made a small mistake, the value of Vc should be, Vc should be equal to under root gl only. Okay, so sorry for the mistake, I will draw it again. So energy at C location, that is the topmost location, is equal to mg into 2l, correct, plus half m Vc square. Now we know that Vc square is equal to gl. Therefore, Ec is equal to mg into 2l plus half m into gl. Right? Therefore, we can write that the value of Ec is nothing but mgl into 2 plus 1 by 2, which is 5. Right? Similarly, we can say energy at point A is nothing but equal to mg into 0 plus half m into v0 square. We know that v0 square is nothing but equal to 5gl. Therefore, acceleration at A, and the total mechanical energy at A is equal to half m into 5gl, which is equal to mgl into 5 by 2. So you can see that by any way we can get the same image. Okay. Now let us just use this concept here. Therefore, what is the energy at B? Energy at B is nothing but mg into L, because only L height is being raised up, plus half m VB square, just equated to mgl into 5 by 2. So if I equate it, I will get, therefore what we can get half m VB square is equal to mgl into 5 by 2 minus 1. Correct? So I just put it in this place here. Okay. Therefore what we can get, we can cancel m and m from here. We can get VB square is nothing but equal to GL into 3 by 2 into 2. So 2 will get cancelled. I just put this 2 in this direction. Therefore, VB is nothing but equal to root 3GL. Fine. So we got the value of VB also, we got the value of V0 also, we got the value of VC also at the locations specified in the terms of gravity and length. Okay. So just again explaining the complete concept. This was a complete circle given to you. Sorry for the example, I cannot make it complete circle. Let us make a small circle. So let us take this to be the circle. Okay, this is the topmost point, this is the bottommost point, and this is the midpoint. Correct? Let us note this point as VA, this point as VP, velocity at this point is VP, and this velocity is VC. The velocity is highest at the lowest point, that is equal to root 5GL. Lowest at this point, which is equal, medium at this point, which is equal to 3GL, and lowest at this point, which is equal to GL. Okay, so as you can see that as we go on moving upwards, the value of velocity keeps on decreasing. Okay, so that was a complete concept. I highly suggest you to directly remember this, because in many of the exams, these values directly come up. Okay, so it will be much easier if you try to remember these results. Okay. Now let us just complete the complete iteration part and move forward. Okay, so we have understood at this location that VB is nothing but equal to under root 3GL. So we calculated the value of V0 also. We calculated the value of the speeds at point B and C. Okay. The next thing is being asked, that is the ratio of the kinetic energies at that is basically KB and KC. So let's calculate it also. So what is KB? KB is nothing but equal to half m into VB square. Please remember VB square is 3GL. So it is nothing but m into 3GL by 2. Similarly, what is KC? KC is nothing but kinetic energy at C, that is VC square, that is nothing but m into GL by 2. Therefore, KB by KC is equal to 3mgl by 2 upon mgl by 2. Correct? mgl getting cancelled, 2 getting cancelled, then we will get the ratio in nothing but 3:1. Okay. Fine. So just iterating it. So the ratio of the kinetic energies at B and C is KB by KC, which is equal to 3 by 1. So at point C, the string becomes slack and the velocity of the bob is horizontal and to the left. Okay. So at point C, the string becomes slack and the velocity of the bob is horizontal and to the left. The velocity is at this direction. Now, it's just a discussion part. Please look at this line also very, very carefully. So if the connecting string is cut at this instant, so let us say it is moving in this way, and now we just cut the string at this location. A bob will execute a projectile motion with the horizontal projection akin to a rock kicked horizontally from the edge of the cliff. So basically what would happen, it would be same in this form. Let us suppose if I have some ball being kept here and it is being pushed forward with a velocity VC. So what will happen, basically it will follow a projectile motion in this way. That is thing only explained here. If I cut the string at this position, because only velocity is being acted upon, there is no other thing being acted upon there. Okay, and the mg will be acting in the complete sense towards in its position, in its complete projectile motion. Okay. Otherwise, the bob will continue on its circular path and complete the revolution. So, if the string is not cut, if there is nothing of that sense, then it will again come downwards. It will again come downwards, and then again go here. And then, if the velocities are being imparted in the similar fashion, there is no another force acting upon it. Only conservative forces are being acting, then it will keep on. The revolution will keep on happening. Or basically, the revolution will get completed. Otherwise, the bob will continue on its circular path and then complete its revolution. Okay. So I think this question is clear. This is a very important question for all the concepts you should be understanding. Okay. So this was the first example. So please try to remember all of these examples here. So please remember the velocity at this location, that is under root 5 gl. That is under root 5 gl. The velocity at this location, that is under root 3 gl. And the velocity at this location, which is under root g. Okay. So I hope this concept is clear. That thing being said, now let us go towards next example, next new topic to be understood, that is potential energy of a spring. Okay. So please understand this very carefully. Very small concept, a little bit understanding of the quadratic concept will be used here. That thing being said, just I will try to start this discussion with a small concept which you already understood in potential energy. So basically, what's a spring? A spirally shaped substance which can even compress. So let us say I compress it. So it is something of this form. And when I remove this force, what happens? It jumps to its original position. Correct? It again jumps to its original position. Correct? So this is basically a spring. As we are physicists, we are trying to understand the physics behind it. What is actually happening? What will a physicist say? A physicist will say that there was a spring. On application of force, basically I imparted potential energy into it. This compressing led to storage of potential energy. Okay. And hence that is the complete concept which you are trying to understand, that what is this potential energy of a spring being had. So it won't be here 3gh, correct? This won't be 3g, it won't be mgh here, okay, because mgh is for a gravitational force. Here, depending upon this value of displacement being occurring, we will understand what is the potential energy being held by a spring. So just a small introduction. Now let us begin with this new discussion regarding the potential energy of a spring. Okay. So the spring force is an example of what? It's an example of a variable force. Quite evident. So basically, what is the meaning of a variable force? That with a change in the value of displacement, let me write also. So a force which changes with displacement is basically called as a variable force. Okay. Fine. So a spring force is an example of a variable force which is conservative. Okay. So please remember this also. So here also we can directly apply the mechanical conservation of mechanical energy. That is the kinetic energy and the potential energy at any location, if and only if the spring force is acting, can be said to be conserved, or basically they can said to be constant. Okay. Right. Moving on. So figure shows a block attached to a spring. Figure shows a block attached to a spring. Okay, let's understand each and every word so that there is no confusion in the future. So figure shows a block attached to a spring and resting on a smooth horizontal surface. So what is the meaning of resting on a smooth horizontal surface? It simply means that there is no frictional force acting. Okay, so I'm just writing it also. So resting on a smooth frictional surface basically means that no frictional force is acting. No frictional force is acting. Okay, fine. Moving on, the other end of the spring is attached to a rigid bone. Okay, so other end is attached here, as you can see. The spring is light. The spring is light and may be treated as massless. So what is the meaning of this light? Basically, the mass of the spring can be assumed to be 0. Okay. Now, in an ideal spring, the spring force Fs. So there will be some force which is acting upon it, correct? That force is proportional to, please look at this definition very clearly. So in ideal spring, the spring force Fx is proportional to x, where x is the displacement of the block from the equilibrium position. Okay. The displacement could be either positive or negative. So either you can put the displacement. So let us say we are trying to push, or basically pull the block here, and here we are trying to push the block. Okay. This force for the spring is called the Hooke's law and is mathematically stated as Fs is equal to minus Kx. Okay, please remember this. Fs is equal to minus Kx. Please remember that the force acting is opposite to the direction of the displacement. Force, or let me write it as spring force. So Fs is equal to minus Kx. Okay, so I can write spring force acts in the direction opposite to the displacement. So I hope it is clear to you. So if let us say that x is positive, then it is quite clear that Fs will be negative. And similarly, if x is negative, then it simply means that the direction of Fs or Fs will be positive. Okay. So the first understanding is you just need to understand that the spring force mathematically, first of all, you should understand it is also called the Hooke's law. And the second thing which you need to understand is that mathematically it can be done as Fs is equal to minus Kx. Okay. This K here is also called as spring constant. Okay. Fine. So it is also written here. So basically, the constant K is also called as the spring constant. Okay. So as we know, so its unit is Newton per meter. So how it is Newton per meter? As F is equal to minus Kx. Therefore, K is nothing but equal to minus F by x. Okay. Therefore, as F is in newtons, M is in meters. Therefore, what will be the unit? It will be Newton per meter. Okay. So the spring is said to be stiff if K is large and soft if K is small. Okay. So you may listen to these words when you will do some of the questions regarding it. So it will written such that a stiff spring is used here, or a stiff spring has a spring constant as some value. So there you can understand that the value of K would be at some range of higher sense, and if it is said to be soft, then it can be said as some smaller. It can be said that a spring constant is small. Okay. Suppose that we pull the block outwards as in figure. Okay. So now please look only at this point here. Just don't see upward, don't see downward. Just look at this position B here. Okay. So here, if x is positive, so let us take that x is positive here. Okay. So what is happening here? We are pushing the block outwards. Correct. So if the extension is xm, so basically if I'm saying that this has moved this location, correct, from its original position, I will denote this as xm. Okay. Then what is the work done by the spring? Okay. So let us calculate the work done here. So work done by the spring is basically F dot dx, which we got. This concept was being proved to you when we were understanding the subtopic. When we are understanding the subtopic, the work done by a variable force. Okay. So work done is nothing but equal to integration from f dot dx from xi to xf. So I'm just putting the value of f as minus kx. So I can write it as nothing but integration xi to xf minus kx dx. Correct? As minus k is a constant, it can be kept outwards. It's minus k integration xi to xf x dx. Okay, x is not a constant, x is a variable here. Now we know that as integration xi to xf, let me choose, okay, fine, that's okay. So x dx is nothing but equal to x square by 2 from xi to xf. So I'll just put the values here. It is nothing but xf square by 2 minus xi square by 2. Okay, that is nothing but equal to xf square minus xi square by 2. Okay, so same thing can I put here. So it can be nothing but equal to minus k times xf square minus xi square by 2. Okay, if xi equal to 0, then the work done will be nothing but equal to minus k xf square by 2. Okay, that is the complete explanation with that. That is how we calculate the work done by a spring force. Okay, so that thing is only explained. So let us say what will be the work done by the spring force. That is nothing but work done is equal to integration 0 to xm. So they just assumed xi to be equal to 0. So therefore 0 to xm fs dx is equal to minus 0 to xm kx dx, which is equal to minus kxm square by 2. M is in subscript. Okay. This expression may also be obtained by considering the area of the triangle as in figure D. Okay, so we understood this also, that as in we can understand the work done nothing but the area under the graph f and x. Okay, so this is nothing but the force f minus kx acting. So if we are going from displacement 0 to xm, so it is nothing but the area this. So how can we say that this area is the work done? Just look at this graph very carefully. So if you look at this graph very carefully, what we can say, what is the area? It is nothing but the area of the triangle here. So what is the area of the triangle here? This area is nothing but equal to half into base into height. So what is the base here? Base is nothing but xm. What is height here? Height here is basically minus k into xm. That is nothing but equal to minus k xm square by 2. Okay, so I hope it is clear how we got this value as minus k xm square by 2. Okay. Next, note that the work done by the external pulling force F is positive since it overcomes the spring force. Okay, so external pulling force, if you are trying to pull something, so please remember here only the direction is reversed. That's all. So the work done by the spring force, please remember, work done by the spring force, because the questions can be asked in this similar manner and you can make mistakes here. So please try to understand this very carefully. Work done by the spring force will be negative, but work done by the external pulling force will be okay. The work done by the spring force will be negative, but the work done by the external pulling force is positive. Why? Since it overcomes the spring force. Therefore, W is nothing but equal to plus K xm square by 2. Fine. So I've explained everything here. Let's move on. Okay. So the same is true when the spring is compressed with a displacement xc. Okay. So there also what we can write simply that it is nothing but minus k xc square by 2 and the external work done is positive. Okay. So here also, so it doesn't depend xc is negative or positive, the square will always positive. But you should remember that the work done by spring should be negative always and the work done by the external force should be positive. Okay. So I hope it is clear. You can even remember this, that the work done by the spring is negative and the work done by the external work is positive. So I can even write it also here. Okay, so work done by spring is negative and work done by external force is positive. Okay, why? Since it overcomes the force, since it overcomes the spring force. Okay. So this thing is also explained. Now, if the block is moved from an initial displacement xi to a final displacement xl, the work done by the spring force Ws will be what? It is nothing but equal to, so as there will be a minus sign here also. So therefore, I just calculated it when I was trying to explain the same concept in the black slide. So there also what we got finally what? It is minus k into xf square minus xi square by 2. So if I put the minus sign inside, I will get it is nothing but k into xi square by 2 minus k into xf square by 2. Okay, and that is the only thing which is written. So we got this thing also, that the work done by the spring force Ws when the block is being moved from a initial distance xi to a final distance x. Okay, So this thing can also be proved using the area again. So let us assume that this was some location xi and this was the final location xi. So what is the area or the work done? The work done will be this. Correct? This will be the work done here. So how can we calculate this work done? So either what you can do, you can just find the area of this location, correct? And minus the area of this small area, correct? So here this will be your xi and this will be your xf. So you can either do this thing or you can just directly find the value of this trapezium, correct? So you know that the force acting at this location is nothing but F is nothing but equal to minus K into xi, and here it's minus K into xf, and here it is xi minus x. Correct? So even if you calculate the answer from this, you will get the same result. Okay? xf minus x. This should be xf minus x. Okay? Fine. So that thing being said, now let us understand more. So what is thus the work done by the spring force depends only on the endpoint. So as it depends on the endpoints, in the starting of the discussion also we wrote that this spring force is nothing but a conservative force. So from that definition also we can say that the work done by the spring depends only on the endpoints, which was the second definition when we were understanding the conservation of mechanical energy. Okay. Specifically, if the block is pulled from xi and allowed to return to xi, so then as it depends only on the endpoint, so it's xi square by 2 minus xi square by 2, which will give you the answer as 0. So I hope it is clear because it depends on the endpoint, therefore the work done will be 0. Okay. So the previous discussion just written in terms of line can be said as the work done by the spring force in a cyclic process. What is in the cyclic process? Going in one direction, returning to the same direction is basically called a cyclic process. Is 0. Okay. So the work done by the spring force in a cyclic process is 0. We have explicitly demonstrated that the spring force is position dependent. Quite evident, we know why it is position dependent, because we just wrote that the force value is nothing but equal to minus kx. So Fs is directly proportional to x, or we can say that it is position dependent. Only as first the hook said that F is equal to minus kx. Second thing is that the spring force does work which only depends on the initial and the final position. So this thing also we understood because as it is a conservative force. Okay. Thus, spring force is a conservative force. Okay, so then hence it is being said that it is also said that spring force is a conservative force. Okay. We define the potential energy Vx of the spring to be 0 when the block and the spring system is in equilibrium position. So at this position, the value of the potential energy is 0. Okay. For an extension or compression, x, the above analysis suggests that what is V of x is equal to under root kx square by 2. Okay. So how did we get this location? How do we get this? If you remember correctly, in the discussion regarding the concept of conservation of mechanical energy, we got that for a conservative force, delta V of is nothing but equal to minus f of x delta x. Okay. So therefore, what we can get that the complete integration of V is nothing but equal to minus integration f of x dx is nothing but equal to minus integration of minus kx dx, minus getting cancelled, and then we can write as kx square by 2. Therefore, what we can write that potential energy is nothing but equal to half kx. So you can understand how we got this result. Okay. So just keep on revising everything, just keep on understanding everything. Then even if you go forward, everything will be understood much clearer. Okay. Fine. So finally what we got that for an extension, so it doesn't depend either we are extending or compressing. Sorry. The potential energy will always be equal to kx square by 2. Okay. So you can also, so I just verified also for you how that dB by dx is equal to minus dB by dx is equal to minus kx. Okay. That is the spring. Moving forward, so if the block of mass m in figure is extended to xm, So let us say we go from this location to this location and is released from this. So at this location now we were trying to hold this block first and then we released it. When we released it, first of all we should know that the total mechanical energy will be same. So that is total mechanical energy at any arbitrary point x, where x lies between minus xm to plus xm will be given by what? Please remember, we can only talk about the range in the mirror form. So we can only talk about range from this xm to this minus xm. We cannot say anything about regarding or relative another portions. Okay. So as it is a conservative force, we can directly apply the total mechanical energy concept at any of these locations. So what we can say? We can simply say that what was the kinetic energy at the position xm? Sorry, potential total mechanical energy is half k into xm square is equal to half k into x square plus the velocity at this location, which is half m e square. Fine. Where we have invoked the conservation of mechanical energy. Okay. This suggests that the speed and the kinetic energy will be max. Yes sir. हाँ सर ठीक है 55 मिनट के बस 20 सेकंड बचे थे सर, इसलिए मैं बस उतना सा और पढ़ा रहा था. हाँ सर, वो मैंने एक टाइमर लगा के रखा था, जब चालू करता 55 मिनट्स का एक टाइमर लगा देता हूँ मैं. बस मैं इतना पढ़ के बस मैं स्टॉप ही कर रहा था सर. ओके. So this suggests that the speed and the kinetic energy will be maximum at the equilibrium position. So what is basically equilibrium position? This is your equilibrium position. Okay. So if we just calculate at this location, what we can say? We can say that let us take this value of x, or we need to find out what will happen when we are starting from this location, releasing the body. So what will happen, or what is the velocity at this location? Let's put the value of x to be 0 here. Therefore, what we can get directly that half k xm square is nothing but equal to half m velocity square. Therefore, half are getting cancelled. We can say directly that this velocity is nothing but equal to root over k by m into x. And that's how we can understand this using the concept of conservation of energy, which is the maximum. Okay, so let me stop the discussion here only. We will again revise this concept. We will again see for different positions and then go on with the further discussions. Okay, so let me stop it here. So we started with the introduction, just a course progress module. We started with introduction. Then work energy theorem is complete. Work and kinetic energy has been explained. Work done by a variable force is explained. Work energy theorem for a variable force is explained. We have understood the concept of potential energy also. We understood the conservation of mechanical energy also. Potential energy of spring has been going on right now, and then we'll move on to various forms of energy, then important concepts such as power and collision. Right? So that thing being said, thank you for this lecture. We will meet in the next lecture. So thank you so much.